subatomic orbitals, the fuzzy spheres, dumbbells, and clover leaves, and wondered, well, why those specific shapes? Where do they actually come from?
Right. It often feels a bit like chemistry magic, doesn't it?
Yeah, exactly. But it's actually pure math. We've got some really interesting material here, taking a deep dive into the connection between something called spherical harmonics and, well, the very shapes of these electron clouds.
That's right. And what these sources are showing is that the shapes aren't just, arbitrary diagrams or helpful pictures. They are the direct, sort of unavoidable outcome of the mathematics describing where an electron is likely to hang out in an atom.
And specifically, these shapes come from mathematical functions called spherical harmonics.
Precisely.
So that's the core idea we want to explore today. How this quite abstract math literally dictates the physical shapes of atomic orbitals, those SPD and F shapes you see everywhere in chemistry.
And it all stems from solving the fundamental equation for electrons and atoms, which is the Schrödinger equation.
All right, the big one.
Yeah. Think of the Schrödinger equation as like the master blueprint for an electron in an atom. When you solve it, you get the electron's wave function, usually written as phase.
Okay.
And this wave function contains basically all the information we can possibly know about the electron's state, its energy, its angular momentum, and crucially for this discussion, its probability of being found at any particular point in space around the nucleus.
So the wave function is essentially a probability map for the electron. Now, what's really fascinating, and a key point in the material we have, is that for an atom, which is, basically a nucleus with electrons in a pitcher field that looks the same in all directions, spherically symmetric, this complicated map can actually be split.
Exactly. It separates very neatly into two independent parts.
Okay.
One part is the radial part. Let's call it r. This part only depends on r, the distance from the nucleus. It's connected to the principal quantum number, and which, as you know, relates to the energy level and overall size, and also the azimuthal quantum number below. So the radial part basically tells you how far out the electron is likely to be.
Makes sense. Distance from the center, what's the other part?
The second part is the angular part, usually called y. This part depends only on the angles theta and phi. Think of them like latitude and longitude coordinates on a sphere centered on the nucleus.
Okay, so direction.
Exactly, direction. And here's the kicker. This angular part y is the spherical harmonic function we mentioned right at the start. Its specific form is determined by two other quantum numbers, L and M. We'll get into those.
Ah, okay, so the math itself just falls apart into distance and direction.
Pretty much, yeah. The complete wave function, r, dia r times y, the math separates the how far from the which direction.
And it's that which direction piece, the angular function y, the spherical harmonic, that really stamps the characteristic shape onto the electron's probability cloud.
That's it. The radial part r, it affects the size and introduces some nodes based on distance, but the actual shape itself, that comes purely from y.
Right. This is where those other quantum numbers you mentioned, L and M, come in. They act as the bridge.
They are absolutely the bridge. They function as parameters within that spherical harmonic function, y, dictating its specific mathematical form, and therefore the resulting shape and orientation of the orbital.
Okay, let's take L first, the azimuthal quantum number. We usually learn this determines the orbital type, like SPDF, and it's linked to angular momentum. The material directly connects L values to these shapes.
It does. For example, take LEO. The corresponding spherical harmonic, mathematically, y euro, is just a constant, a single number.
A constant, like the number 2, or 1 over pi, something like that.
Sort of, yeah. It's related to 1 over the square root of 4, actually. But the point is, it has no a or ot in it. It doesn't change with direction.
Ah, so if the function value is the same, no matter which direction you look,
the probability of finding the electron is the same in all directions. Perfect spherical symmetry.
that's the s orbital.
That's your s orbital. Zero angular dependence in the math leads directly to a spherical shape.
Okay, that makes perfect sense. So what about L1?
Well, for L1, the spherical harmonics, the y functions, get more interesting. They do depend on the angles in L1 now. And quantum mechanics has rules that say for L1, there are exactly 3 possible values for the next quantum number, m.
Right.
And this mathematical fact that there are 3 possibilities tied to L1 leads directly to the 3 distinct dumbbell shapes of the p orbitals.
Okay, wait, so L sets the general shape type, like L1 means p-type dumbbells, and then M tells you which of the 3 p orbitals you get. based on its orientation.
You've got it. That's exactly how it works.
Cool. So L2 must be.
For L2, the math for the spherical harmonics we row gets even more complex, more angular dependence. And again, the rules of quantum mechanics give us a specific number of allowed m values for L2.
Which is 5, leading to the 5 orbitals of the cloverleaf ones and the other more complicated shapes.
Precisely. And then for LO3, the complexity increases again, giving spherical harmonic Haro that map onto the 7 orbitals, with those really intricate geometries you might have seen pictures of.
Oh, okay, so that magnetic quantum number, you said it relates to orientation. How does specifically determine how many orbitals there are of each type and which way they point?
Yeah, this is really elegant. It comes from a simple mathematical constraint. For any given value of L, the allowed integer values of m can only range from s through 0 up to plus L.
Oh, right. I remember that rule. So for L1, m can be -1, 0, or +1, 3 values.
Exactly. And for L2, m can be -2, -1, 0, +1, or +2.
And total number of values is always 2L plus 1.
Always 2L plus 1. The simple formula is why you get that specific count for each orbital type. For L0s orbitals, 2 times 0 plus 1 is 1. Just one possible m value, m0, so 1s orbital.
Makes sense.
For LO1p orbitals, 2 times 1 plus 1 is 3. 3 m values, -1, 0, plus 1. That's your 3p orbitals.
BXPOIY.
For LO2d orbitals, 2 times 2 plus 1 is 5. 5 m values, 5d orbitals. And for L3 orbitals, 2 times 3 plus 1 is 7. 7 m values, 7 f orbitals.
That's actually pretty profound when you think about it. That simple formula, 2L plus 1, just pops out of the map for these spherical harmonics, and it dictates the basic structure of electron shells everywhere. It's not arbitrary at all.
Not in the slightest. It's a fantastic example of how seemingly abstract mathematical rules lead directly to observable physical structures. Each unique pair of L and M gives you a specific spherical harmonic function. U sub lim sub, and that means a unique spatial orientation for that particular shape type.
Like for the p orbitals, LO1, the different m values, -1, 0, plus 1, somehow correspond to the orientations along the x, y, and z axis.
That's right. The specific mathematical forms of y, L over a, L, O, and y, or combinations of them, technically, to get the real valued px, pi, pz shapes we usually draw, point along those axes.
Okay, so we have the underlying math Schrödinger equation, separating the wave function, identifying the angular part as spherical harmonics. We have the parameters L and M that fine-tune that math and predict the number and orientation of shapes. But what are we really looking at in those pictures, the fuzzy clouds? The material says it's about probability density.
Yeah, exactly. You're not seeing the electron's path or anything like that. You're seeing a map of where the electron is most likely to be found if you were to measure its position. This probability density is calculated by taking the wave function and squaring its magnitude, which we write as ph.
Right, the square of the wave function.
Yeah.
And the source material makes a really critical point here, doesn't it? Since the radial part, R, only affects the size and distance-based nodes.
The characteristic shape you visualize is determined entirely by the square of the angular part.
So it's K sub lim's the ball. The shape is literally the shape described by the squared spherical harmonic function.
That's the essence of it. The shape is a direct plot of that angular probability.
Which also explains the nodes, right? The places where the electron is never found.
Exactly. Nodal surfaces.
Yeah.
These are regions where the probability density drops to exactly 0. And the material points out that the angular nodes, those flat planes you see cutting through p orbitals, or the conical surfaces in some d orbitals, are a direct consequence of the mathematical properties of the spherical harmonics y themselves.
And there's that simple rule again. The number of these angular nodes is just equal to the value of L.
Spot on. Think about it. S orbitals, L, 0. 0 angular nodes. It's a sphere, no angles where probability is 0.
Okay.
P orbitals, L1. They have exactly one angular node, which is typically a plane passing through the nucleus, separating the two lobes.
Right, like the YZ plane for the PX orbital.
Precisely.
Yeah.
D orbitals, L2. They have 2 angular nodes. These can be 2 planes, like in the cloverleaf shapes, or sometimes a cone, but always 2 because L2. These nodes aren't just artistic additions. They are mathematically required features of the corresponding Y function.
Wow. Okay, so bringing this all together then, the big takeaway isn't just that spherical harmonics happen to look like orbital shapes. It's much deeper.
It is. The relationship is one of direct mathematical identity. Spherical harmonics are the functions that describe the angular behavior of the electron's wave function.
And therefore, they are the source of the orbital shapes and their orientations.
Absolutely. We started from the Schrödinger equation, saw how the solution splits for an atom, identified that angular part as the spherical harmonic, and then saw how the quantum numbers L and M act like dials on that mathematical function to directly set the shape type, the number of orientations, and which way they point.
It really shows you how this, well, quite elegant mathematical framework underpins the actual structure of atoms, the building blocks of all the chemistry around us.
It's where abstract math becomes tangible, physical reality. It's pretty amazing.
It really is. So here's a final thought for you to mull over, something that comes right out of the material we looked at. Think about that simplest case again, the s orbital.
It's spherical harmonic. Way-a-yo is just a constant. No dependence on direction, no E or anywhere in the formula. How does that complete lack of angular information, just a simple constant number, mathematically enforce that perfect uniform spherical shape for the electron's probability cloud? It's simple yet profound, isn't it?